All right, so we're gonna do an example of the linear factorization theorem. So we're gonna write this as a product of linear factors. So let me go back to that and just kind of remind ourselves what that is. So linear factorization theorem says basically any polynomial of degree n will have precisely n linear factors. So let's go ahead and do that one. So we have a third degree polynomial, so it means we're going to have 3 zeros and 3 linear factors. Easiest way for us to kind of get this started is to see if there are any real zeros by graphing it. And we see that there is a single real zero at -5. So let's go ahead and divide that out. So let me do that. So -5, we'll divide that factor out. Remember, the factor we're talking about with this one is going to be x plus 5. That is the linear factor that would give us this 0. Our coefficients here are 1, -3, -15, 125. Multiply, add, multiply, add, multiply. And awesome, remainder 0. That's what we were hoping for. So this had only one real zero. So our other zeros are either going to be complex or imaginary. So we need to figure out what those are. This is a quadratic, x squared minus 8x plus 25. That is not going to be factorable. I already know that basically based on there being no real zeros. So I'm going to go ahead and go straight to quadratic formula. Opposite of b, the opposite of b, plus or minus the square root of b squared minus 4 times 1 times 25, so that's minus 100, all over 2a. Right here we get -36 when I do that 64 minus 100. So this is going to be x equals 8 plus or minus 6 root I over 2. Those are both divisible by 2. We're going to get 4 plus or minus 3i. So those are our remaining zeros, complex numbers, 4 plus 3i, 4 minus 3i. And we're going to go ahead and write out the linear factors that would be associated with that. So x minus 4 plus 3i. And then x minus 4 minus 3i. So there are 3 linear factors for this third degree polynomial. Notice how we wrote the complex factors out there in parentheses, subtracting the 0. Same way this one could be written as x minus -5, right? We just kind of shortcut that and write it as plus there. All right, let's go ahead and see what else we can do with these theorems. Here we have a 4th degree polynomial, and we know one of these zeros. So we know one of the 2 right there, or one of the 4, there's 4th degree. We also know based on the conjugate pairs that this would also be a 0, because complex zeros always come in conjugate pairs. And I can see the other ones here on the graph. So that's all 4. Now I'm going to do this algebraically here. I'm going to show that these are zeros and then solve for this one algebraically as well. So let's go synthetic division. Let's divide out both of these solutions. All right, -2, 10. Hold on, let's see. -2. All right, so bring down the 1, -2. Add those together, -3, 10, 16. Add these together, or multiply these together, -32. Multiply here, we get 60. Okay, yeah, remainder 0. I was worried there for a second that I had made a mistake, but nope. Remainder 0, we're good. Now I'm going to do this again with my second root of 3 on this reduced polynomial. Remainder 0. That's supposed to be positive 10. There we go. All right, and now we have our reduced polynomial, x squared minus 2x plus 10. And since we know that is going to give us the other two solutions, our complex solutions, we will just go ahead and do quadratic formula with that. When we know our solutions are going to be complex numbers, that's when we want to use quadratic formula. All right, so x is equal to the opposite of b plus or minus the square root 4 minus 4 times 1 times 10, which is minus 40, all over 2 times 1. That's going to be negative 36 again. And when we take the square root of that, that's going to be 6i over 2. And then divide that through, we get 1 plus or minus 3i. So that does match our two complex roots here. So here are our 4 zeros, our 4 roots for this particular polynomial. Now, obviously, we were able to confirm those much earlier, but this would be our algebraic methods. All right. Here is another one, and this one's going to be pretty challenging. So looking at this one, it's a third degree polynomial. So now there's 3. We have one complex, so we actually know another one as well. So putting those two together, I have my third one here. This looks like an irrational solution. So for me to fully figure this out, apologize, this is also supposed to be minus. There was a mistake in this. For me to find this exact value, I need to do synthetic division with these complex answers. So I'm going to go ahead and do that. It's going to be pretty detailed, a lot going on here. Okay, so let's see what we got here. We have, again, I'm going to change this. This is a minus. I made that mistake when I was copying this problem out. So we have 1 minus I root 3. We're dividing out from this polynomial, which is 1, negative 4, 8, negative 8. Okay, bring down the 1. Multiply this by 1. So that's the easy one. Add these together. Here is where things start to get messy. Now I need to multiply these two things together. We got 1 minus I root 3 times negative 3 minus I root 3. Multiply that out to get negative 3. Negative I root 3. It's really negative 1 I root 3. And then we get plus 3 I root 3. And then we get positive I 3. So positive 3i squared. Remember, I squared is negative 1. Okay, so that's actually going to be, this all becomes minus 3. Negative 3 minus 3, negative 6. Negative 1i root 3, 3i root 3, that's going to be plus 2i root 3. Okay, so that's what's going to go here. Negative 6 plus 2i root 3. Add these together. We're getting 2 plus 2i root 3. Okay, I need some space here to multiply things out again. So now we're multiplying this times this. One times 2 is 2. 1 times that is plus 2i root 3 minus 2I root 3. And then here we have negative 2 root 3 is 3. So it's going to be negative 6I squared. Okay. That ends up being plus 6. Let me simplify that. So 2 plus 6 is 8. 2I root 3 minus 2I root 3, those actually cancel. So we end up with 8, remainder 0. Perfect. Remainder 0, got that. Now we have our reduced polynomial right there. So I'm going to erase some work here. I need to do synthetic division with that one again with my conjugate pair for this. So that is 1 plus I root 3. We know this also to be a root, and we're going to divide out that one. So, okay, bring down the 1, multiply this by 1. Oh, that's nice. Those will cancel. We'll end up with negative 2. Okay, negative 2 times this. That's actually also pretty easy. That's negative 2 minus 2I root 3. And that's a 0. Sweet. So there we go. Got rid of that. And here we go. We have our other root, which is x minus 2. Sweet. So that means that x equals 2 is our third root. Oh, so I see what happened. When I graph this, let's go back to it. Let's go back to that graph. I graphed the wrong function, which kind of messed things up from the beginning. That's okay. If I graphed this proper function, I think I would have seen this root. Oh well, no big deal. We got the answer in the end. Pretty difficult stuff, though, to be honest. Pretty tedious work. All right, let's go ahead and clear this out. And let's keep moving on. Okay, so when you are factoring, something that's going to happen a lot of times when you encounter polynomials with complex roots is you're going to end up with what's called an irreducible quadratic. So something like this. It's where if you looked at the graph, it wouldn't have any x-intercepts. If you tried to factor it, you wouldn't be able to factor it with the real numbers. The only way to solve this, the only way to find the zeros for this is using quadratic formula. If you ever end up with one of these that are irreducible over the reals, it's not factorable, you can't graph it and find the zeros, you gotta use quadratic formula. That's gonna happen when we have complex roots. All right, so let's go ahead and do a couple more here. So we want to write the equation of a polynomial with the following zeros. Okay, so these all are going to help me write some factors. Remember, whatever the 0 is, I can do x minus that 0. How in complex form. These are imaginary, so whatever. So this would be x minus I. This would be x plus I, or minus a negative, but plus is easier. Same idea here, x minus 6I, x plus 6I. If I multiply these all out, I will get a polynomial in standard form with only real coefficients. So let's go ahead and do that. These are conjugates, so we know they follow difference of squares pattern. They're going to be x squared minus I squared, but whatever this is. But let's just go ahead and multiply them out. We get x squared plus ix minus ix minus I squared. These cancel. We end up with x squared plus 1. I'm going to find it actually easier to multiply these two together, multiply these two together, and then multiply the results. It's just going to be a bit easier. So we end up with this, which ends up to this. And now let's do the other side. So we got x times x, x squared, plus 6ix minus 6ix minus 36i squared. So that's actually going to end up being x squared plus 36. Then I can multiply their results together. X to the fourth plus 36x squared plus x squared plus 36. These can go together, so we end up with x to the fourth plus 37x squared plus 36. There we go. That is the polynomial that is equivalent to this with only real coefficients. And that works again because these are conjugates when we multiply them. All right, last one here, same concept that's happening, except we have these two complex roots. I'm going to go ahead and multiply these out because that's going to be a little bit more complicated. And this one I'll leave for the end, right? This one's just going to be x minus 6. I'll multiply by that later. These are going to be x minus negative 5 plus 2i. And then x minus negative 5 minus 2i. Okay, so let's multiply this. We get x times x times that. So that's going to be negative x, negative 5 minus 2i. We'll deal with that in a minute. And then we have negative, sorry, that was this times this. Now we're going, so this times x, that's going to again be negative x times negative 5 plus 2i. And then we have positive negative 5 plus 2i times negative 5 minus 2i. Okay, more algebra here. This is going to be plus 5x plus 2ix plus 5x minus 2ix. Now when I multiply these, negative 5 times negative 5 is 25. That's going to be negative 2i squared, so it's going to be plus 4. Okay, putting some things together, we have x squared, 5x, no, 10. This 2ix and negative 2ix cancel. So this is going to be x squared plus 10x plus 29 times my remaining factor, x minus 6. Yeah, that's x cubed plus 10x squared plus 29x minus 6x squared minus 60x. 6 times 29, 6 times 30 is 180. 6 times 29. $174. Okay, combining like terms, my final answer should be x cubed. 10x squared minus 6x squared is 4x squared. 29x minus 60x is minus 31x minus 174. That would be with only real coefficients. All right, and that's it.